Next on our agenda, we have a presentation from Stephen Seamy, a program manager at RTX Corporation, titled A Harmonization of MOSA OSAs, One Weapon System, and the Use of SOSA, WOSA, and FACE Technical Standards. I can help you with the acronym challenge here. Again, MOSA is Modular Open System Approach. OSAs are Open System Architectures. And the standards acronyms are Sensor Open System Architecture, Weapons Open System Architecture, and Future Airborne Capability Environment Technical Standards. Next generation advanced weapon systems will need to include a mixture of Department of Defense recognized open system architectures and government reference architectures. This presentation introduces open system architectures, their role within the fundamental principles of the modular open systems architecture approach, and a conceptual integration of 3 Department of Defense recognized OSA technical standards, the SOSA technical standard, the WOSA technical standard, and the Future Airborne Capability Environment FACE technical standard. Stephen will first discuss the contributive role of what model-based systems engineering does within the MOSA lifecycle and the digital ecosystem environment, and he'll identify benefits of how the open system architectures and model-based systems engineering approaches can speed development, and he'll explain how they support the delivery and sustainment lifecycle of complex systems of open architectures. He then provides an example implementation use case using the 3 standards that are logically combined, and he'll identify a status of how close the MOSA community is today to actually realizing this notional use case. He'll introduce business processes and technical practices that enable a modular open systems approach, describe how the harmonization of these 3 open system architectures serve as a competitive aid when you're soliciting for interchangeable open system architecture components from multiple vendors, and how it supports a model-based acquisition process developed using the actual open system architecture implementation models. So this is getting very close to a real-world example of how we can integrate, provide portability, interoperability, and achieve the quality attributes that Nick Borton mentioned in his presentation earlier. Stephen Seamy is a program manager from RTX Corporation and currently serves in roles as a weapon open systems architecture engineer and a digital engineer for Raytheon, where he performs on advanced missile system technology programs. And he also serves as a MOSA and WOSA instructor, developing and delivering technical content for Raytheon's MOSA Center of Excellence. Stephen is recognized as an industry subject matter expert of the modular open system architecture approach and open system architecture standards with over 30 publications. He has also worked with the advanced aviation industry for the U.S. military and space industry for 34 years.
Okay, good morning or afternoon. I'm Stephen Seamy, recording the FACE and SOSA virtual TIM presentations. Our paper is titled Harmonization of MOSA OSAs, One Weapon System, and the Use of SOSA, WOSA, and the FACE Technical Standards. My other co-authors are Jonathan Kane, Dr. Joyce Tongar, and Al Stussy. So harmonization of OSAs, the premise of the paper is that next generation advanced weapon systems will include a mixture of DoD recognized open systems architectures and government reference architecture. The paper that we're writing introduces the open systems architectures and their roles within the fundamental principles of modular open systems approach, more known as MOSA, and then a conceptual integration of these 3 recognized DoD standards. That'll be SOSA, Sensors Open Systems Architecture, WOSA, Weapons Open Systems Architecture, and FACE, Future Airborne's Capability Environment Technical Architectures. Starting with the premise of WOSA, to set the context, will begin with an introduction of MOSA, lead into the introductions of the three open systems architectures, and then conceptually integrate the three into one weapons system. Okay, so modular open systems approach. Key into on the words, both the first and the last, modular and approach, that's bookmarked by open systems in the middle. MOSA is an integrated business strategy and technical strategy with a reference to open systems architectures, and that'll be principle number 4. It's a DoD preferred method of implementing open systems architectures, and it's required by United States laws for all major defense acquisition programs approved after 2019. And throughout the briefing, we have links to the references that are in both the paper and the presentations at the bottoms for readers to follow on. While modular open systems approach is a new to many, it's aligned with the more known 5 principles with the lifecycle V process phases. So the principles across the top and establish an enabling environment is basically your capturing your requirements in your digital ecosystem environment, and that's a group of interconnected information technologies. Module number 2 is your modular design, and you can see at the bottom it's designing for change because they want to remove and replace these modules for both a technical refresh and obsolescence issues. Principle number 3, key interfaces, is your interfaces, and what the government wants is to own the interfaces so that they can allow for future technological refresh and address obsolescence issues. It's a matter of protecting its investment, and it's actually protecting the taxpayer's investment. Principle number 4 prescribes open systems architectures like SOSA, WOSA, and FACE technical standards, and it also provides guidance on how to do the design for these architectures, including interfaces and context for open systems architectures conformance. And the last one is certified conformance. What you'll see more newer ones like WOSA is in the certifying components, they'll actually have you do a third-party domain swap where they'll remove and replace an entire module. So I placed it over top of purposely the modules 1, 2, and 3. So the requirements, the design, and the interface needs to be done with the artifacts in order to remove and replace an architecture. So we'll go into now the 3 recognized open systems architectures. First and foremost, no particular order, but it's left to right in the actual conceptual integrated weapons system that we do. The first one is SOSA. And the tables from left to right will show the objective architecture, the tasks that are required through developing the architecture, and other software development activities. So the first one, SOSA, specific to military weapons and sensor systems, including advanced seekers for missiles. It is a broad scope of systems architectures, including EO/IR, radar, electronic warfare, signals and intelligence, and communications. So the objective architecture, you got a figure there, and the reference is at the bottom for the SOSA architecture. Basically, the tasks are to figure out the scope, layer in custom algorithms to achieve the behaviors of the seeker or the software that you're implementing. Underneath that is certified conformance. SOSA out of the 3 is the future state. They're developing that conformance program as we speak. And on the third side there, they identify the modules. And if you're familiar with seeker design, these should be you got the receiver, the exciter camera, the image preprocessor, and the signal detector and extractor and the tractor. The next open systems architecture is WOSA. WOSA is a specific design for advanced weapons systems like missiles. The architectures are associated with standard interfaces that are purposely aligned with missile architectures. And the figure shows the domains that are required for that. The WOSA standard is developed and maintained by AFRL with support from consensus from industry. And instances of WOSA are verified for conformance by the group called the MOATEL. That's the Modular Open Architecture Test and Evaluation Lab. So the idea for WOSA is to determine the applicable scope. You may not need all the domains for that you match them to your weapon system, and then layer in the custom algorithms. Certification is identified here. You'll take your engineering development models and independently verify them through the MOTEL test group, and then deliver the implementation to the architecture. Domains, as identified, they need the domain spot for the removal and replace. So you'll need development kits, including all the artifacts for that demonstration. And then thirdly is the Future Airborne Capability Environment Technical Standard. FACE is a standard that can be applied to military or commercial aerospace systems like military aircraft, commercial aircraft, or even oil refineries. FACE approach is to develop a technical standard for the software common operating environment designed to promote portability and create software product lines across the military aviation computer. So following along with the other ones, we have the FACE reference architecture. Again, you determine the scope that you need to implement for your standard. In terms of the FACE, they have 5 particular segments identified with the different colors: PCS, TSS, PSSS, IO, and the OS. You figure what you need to do to implement the capability or architecture. You layer in the custom algorithms and logic for the FACE segments. And then certifying conformance out of the 3 faces the most mature conformance program. The developers have access to the consortium's conformance test suite. That allows them to develop and verify the interfaces as they're developing. And then at some point, they contract with a FACE verification authority. If the UOC passes the verification, then they contract with the conformance authority and pass that, and then they can label themselves as FACE conformant. A note on the right-hand side, if you're on segments, the PSSS and PCS, you have an additional requirement to identify the data model. That's the data, that logical data that traverses through the TSS segment. This differs quite a bit from WOSA, where WOSA, they actually have all of those interface messages defined. So this is a little bit more open, but you have to accommodate it with a data model. So let's get to the fun stuff. How do we integrate a weapons system of 3 complementary OSAs? Well, we have to combine the objective architectures of the different ones. We have to integrate those logical data models so that they align. And if airworthiness is required, we have to combine the artifacts from the individual components into one. And that's typically following guidance of AC 2148. The notional use case that we have for integrating this is one weapon system with technical architectures for SOSA. We're going to have a SOSA seeker on top of a WOSA missile system, captive carried and launched by a FACE aircraft. Now, in order to help people along, I've put links into examples of these that you can actually read and see example implementations of both a SOSA sensor, a WOSA missile system, and a FACE aircraft. Integrating the logical messages between different OSAs. Paper goes into much more detail. But basically what we're looking at, and the data flow from this particular figure is from left to right, right to left, is taking the data from the WOSA weapon system boundary into the SOSA open system. So you're going from blue to white. The information that is needed from the open system includes the navigation domain and the target state estimator domains. And so essentially we've got an alignment between the WOSA and the SOSA domains there. The key in the arrow there is to make that boundary either align 100% or make it thin as possible. So fortunately, we have open system architecture members that span membership across these OSAs, and they have anticipated the need for doing integration across, and they've actually started aligning this. So this particular mapping here, the standards between WOSA and SOSA are almost 100% aligned. The TIM paper, you can look at the reference there to see more on this alignment, but the actual tin paper contains 28 references, and they're all linked so that readers can get access to additional information. Benefits of OSAs and their well-defined interfaces. Now, starting with the definitions that the Defense Standardization Program gives us, MOSA is an approach that integrates the technical requirements with contracting mechanisms. Again, it's modular approach with the OSA in the middle. And then allows for rapid evolution of capabilities and technologies throughout the product lifecycle and beyond, and the use of architectural modularity, open system standards, appropriate business practices. The benefits included the list here: significant cost savings, schedule reduction, rapidly deploy new technologies, the opportunities for technical upgrades and refresh. And I agree with those top three. Once you've developed a OSA product line, you can actually achieve the benefits of these. And the interoperability, including systems of systems, is essentially what we've illustrated on that conceptual integration of those three OSAs. The other benefits, including during the sustainment phase of the major system. And primarily in your digital ecosystem, you'll have the models, all the requirements and designs. So if there's any changes, you change the model and generate that. Additional benefit, and it's highlighted more in the paper, is the automation of auto generation of code right outside of the data models, the testing that's outside of the models, and the artifacts, including documentations that need to be delivered to the customer. Authors and reference documents. Myself, I have 30 years in the military aviations. I've joined Raytheon just recently in system engineering, system design, and architecture for the effectors. My co-authors there, both Jonathan and Al Stussy, they lead the Center of Excellence for MOSA for Raytheon. And then Joyce, Dr. Togar, she just got recently promoted to Senior Technical Fellow. It happened during the publication of this paper. We've included links to each of these authors if you guys want to know more information about the contents of the papers. And here's the list of references within this particular presentation, but as mentioned before, the full paper, which listed on the bottom, has 28 references and they're all linked. So with that, since it's a virtual thing, we won't be taking any questions, but again, you have our links and you have access to the emails to ask any questions to these authors. Thank you very much. Stephen, see me out here.